conservation of linear momentum. It means that the momentum initial has to equal momentum final. That's all. P initial has to equal P final. This is the mathematical expression that we use whenever we have conservation of linear momentum. What's this mean? It means that the momentum final minus the momentum initial has to equal 0. All I did is I moved the P initial to one side of the equation and took the difference. And what's this? This is the delta P equals 0. Recently we have introduced Newton's second law in terms of change in momentum. Let me write down that expression. The net force or the average force equals delta P over delta T. If you want the momentum to be conserved, which means the delta P you want it to equal 0, the only way the delta P can be 0 is when the F net is going to equal 0. And this is the condition that we all must know that causes the momentum to be conserved. In order for the momentum to be conserved, the net force needs to be 0. Now let's make sure we understand the meaning of this. The example that I have on the side is two masses M1 and M2 colliding. It's possible that one of the masses is at rest. And let's discuss exactly that example. One mass is going to hit a second one at rest. Mass 1, here we go, moving with a velocity v1, is going to collide with the second mass M2 initially at rest. M2 right here, its v2 is equal to 0. Let's focus on mass 2 for now. Mass 2, before the collision, its momentum is 0 because it's not moving at all. Immediately after the collision, for sure it's going to move. Therefore, the momentum initial and the momentum final before the collision and after the collisions for mass M2 are not the same. What's that mean? The momentum is not conserved for M2. The same thing can be said about M1. M1 is moving with the velocity v1. Immediately after the collision, for sure it's going to move with a different velocity. Therefore, its own momentum is not going to be the same before and after the collision. What is going to be the same, therefore? The momentum before and after the collision of the entire system, that includes M1 and M2, is the one that is conserved. The entire system. How do we detail this mathematically? Here's how we do it. First, assuming that the momentum is conserved because the net force is equal to 0. Now, we are going to use the conservation of momentum. P initial equals P final. Let's detail this one so we understand. The initial momentum is the momentum for both masses. So basically you have this. M1 V1 before the collision in a vector form plus the momentum of the other one, M2, also in a vector form, must equal the momentum of the two after the collision, the two masses. M1 is going to move with different velocity. I'm going to call it V1 final. Plus the momentum of 2 times its own velocity after the collision, which is V2 final. This is how you're going to write down the expression for the conservation of momentum. The entire system has its momentum conserved, not the individual parts. There are two types of collisions that we would like to detail for you here. Number one is that one that is elastic. We call it elastic collision. In elastic collisions, not only the momentum is conserved, P initial equals P final, the same way I detailed it earlier, but also the total energy of the system is conserved. This is the starting point. I would like you to really pay attention here. The total energy before equal the total energy after. What's the total energy? The total energy is a combination of kinetic plus potential. KE initial plus PE initial equals KE final plus PE final. So keep in mind the conserved quantity is the total energy. This equation can be dramatically simplified by dropping the potential. Potential initial and potential final are equal for one simple reason. When a collision happens, the initial is just before the collision happened and the final is just after the collision is completed, which means the MGH for initial is the same as the MGH for final. They both share the same height. Therefore, you drop the PE's like this, and the final relationship that is simplified is going to look like KE initial equals KE final. One more time, the conserved quantity is the total, but because the potential initial and the potential final are the same, that equation is reduced to a simplified form where only the kinetics are the same. The other type of collision that we will introduce for you are called inelastic collisions. Those collisions which are inelastic, they always result into damage in the objects involved, such as cars colliding, leaving a lot of damage behind. And because of that, the total energy cannot be conserved anymore, because some of that energy has been converted into heat and damage, etc. The only conservation law that is true if the collision is inelastic is the momentum. P initial equals P final. You cannot, in these cases, equate the energies because the energy is not conserved. There is a particular case in inelastic collisions when objects collide and stick together. This one is called completely inelastic collision. If that is the case, this is how you go into detail the equation. You're going to say M1 V1 plus the other mass involved in the collision, M2 V2, and since the objects are going to collide and stick together, they become one unit. M1 plus M2, both of them moving together with the same exact velocity. I'm going to call it V final. So this case here is for that specific one, which is completely inelastic where objects stick together.